Good morning, dear students. Welcome to session 5 of the first module in this subject, computer organization and architecture. So in the previous session, we have discussed about memory, big and little endian schemes, and overflow conditions, etc. So now we'll try to concentrate on how do we write instructions and programs and store it in memory, and what are the different notations available for doing this. Okay. So as we all know, in the beginning, I have told you it's a von Neumann architecture. That means a program is stored in the memory and computer performs its task according to the program stored in the memory, right? So this is called as a von Neumann architecture, basically. And program is a set of instructions written to perform a specific task. And what are the types of operations is generally done in a processor? You know, it's a data transfer between memory and processor registers, or arithmetic and logic operations on the data, program sequencing and control. What is that? We'll discuss. And then, of course, I/O operations, like you want to print something on a monitor, or you want to read from keyboard or from a sensor or something. So any such kind of I/O operation. So these are the four basic types of operations performed in a computer, right? And to illustrate these operations, we need to know how to represent the operations and operands. Okay, so there are two types of notations. One is known as register transfer notation. Other one is known as assembly language notation. Okay, so we'll go to register transfer notation. Okay, RTN, or it's also called as RTL. Okay, so here what we do is we try to identify a location by its name, like a set of English letters like NUM, NUM, or LOC, location, something like that. Okay, that name will indicate the memory address. So just in the previous session, if you remember, I told memory address is like 2000, 2004, something like that I showed, right? And since we do not know the physical address of the memory anytime, as a user, we'll not be knowing this, because this is a part of operating system to assign memory and all. So instead of using this absolute numbers as addresses, we try to provide some names. For example, this is like location, LOC, and this is naturally LOCN plus 4 then. Or any other name of your choice you can use. It's a set of just English letters. For example, you can call this as some N, U, M, NUM, or any name like that. Okay. And processor registers are indicated by uppercase alphabets followed by a numeral. Usually we use the R alphabet. So suppose you have two processors in a register, in a two registers in a processor, then we call it as R1, R2. You have three registers in a processor, then you can call it as R1, R2, R3, etc. So you have certain notations in RTN to represent. Okay, this is how we try to do that. Then all RTN statements will have an arrow symbol. See, all the statements and the operations means what? There is a source and there is a destination. Suppose you want to copy data, say from your pen drive to your hard disk. So your pen drive or USB is your source and the hard disk is your destination, like that, right? So for any of such things, in RTN notation, we follow an arrow symbol. Left side of the arrow is the destination and the right side of the arrow is the source. For example, you can see here it's written. I'm just highlighting this. You can see here R1. Arrow mark, left arrow, always left arrow. Please remember that, always left arrow. Okay. Always left arrow. Then right side is always the source, we said. Say there is a square bracket around this name NUM. It means the square bracket indicates the content of the source. Okay. So copy the content of the memory location num to register R1. So this is one. Another example is shown here, R3. Arrow mark R1 plus R2. That means add the contents of the registers R1 and R2 and store it in R3. Okay, something like that. So the arrow mark is an important notation in RTN. The right side is always the source. Left side of that is the destination. It's easy to understand, but cannot be used to represent machine instructions. That is the biggest drawback of the RTN notation. So we go for assembly language notation. Okay. So in the beginning, when I talked about softwares, if you remember, I have talked about high-level language, assembly language, and machine language. So assembly language is also for the user to write his code or program for his task, but it is not as flexible as high-level language like C, C++, Java, or anything. Okay. So here we use English like words called as mnemonics. Mnemonics. M is silent there, MNEMONICS, mnemonics, to represent the operation. Suppose like move, add, sub, mult, etc. So whereas in C programming, it is easy. Suppose you simply write A plus B with an operator, you know that A is a variable, B is a variable, and plus is the operator. So we do not have that operator or anything over here. This operator symbol is replaced by a word like this, okay, in assembly language. So that means this is called as the mnemonic or a command actually. So which we will be using for writing our code or our program, okay. So how do you see this? You can check here what is written. So I'll just highlight again. Suppose you write MOVV move num comma R1. What is the meaning? So whenever we write assembly language notation, the first we represent source, then we represent destination. Okay. So what is this? It is same as the R1 arrow mark num in RTN. That means you are copying from num to R1 data in memory location num to register R1. Okay. But source is specified first. Remember that. Similarly, here when I say add R1, R2, R3, you are trying to add the registers R1 and R2 and store the result in R3. So rightmost what we write is always the destination. Okay. First we show the source and then write the destination. Okay. One of the major drawback of assembly language is it's not portable. That means we call it as hardware dependent. That means all these processor, this register names, etc., are for that particular processor we have to use. Suppose a processor has the register names as A, B, C, etc., but I try to use R1, R2, R3, then I cannot run this program on that processor. So it's always hardware dependent. So you cannot port it. That means an assembly language program written for one particular processor may not be executed as it is on the other processor. You may have to make modifications to that. So it's not so easy. Whereas a high level language like C or C++ or Java code, what you write, can work on any laptop or any desktop, irrespective of which manufacturer has given the hardware to us, right? So they are called as platform independent, whereas assembly language is platform dependent, okay? And the CPU has a special register called accumulator and several general purpose registers also, which can be used for operation. So when we try to write the program, we will try to know how exactly this can be done. Okay. Now coming to a very important topic in this session, instruction formats. Okay. So an instruction is a command basically, as we have already seen, to the processor to understand something, to do the operations. And this command is for the processor is in machine language or binary, that is zeros and ones. But for the user, we are writing now assembly language program. So command for the user is now knowing the mnemonics, what is required to represent that particular operation. Okay. So syntax, the first one is the three address format, three address instruction format. So how are the syntax? You have an operation followed by source one, source two, comma, destination. Okay. So this is the syntax of, say, all the instructions, just like your C programming language, you have a proper syntax to write, no? Like int x assigned with 25, suppose you write, you can't interchange any of these, right? You need to write in the same way. So there is a proper syntax to write. Similarly, in assembly language also, there is a proper syntax to write. So the first one you have to write is the mnemonic followed by source operands. And at the end, you should give the destination operand. Okay. So this is, you can just check here. For example, I write this way. Suppose I want to perform this operation, Z equal to X plus Y, let us say. Okay. How to write that in assembly language? Add, because this plus is the operation which I write first. Then what you are supposed to add? Source you have to give, X and Y you want to add. So X comma Y, you have to store that result in Z. Okay, so the Z is at the end here. So add the contents of X and Y and store it in Z. Okay, and usually when we write these English letters like X, Y, A, B, C, etc., they are referring to memory addresses or memory locations. Okay, but whenever I write R1, R2, etc., they refer to the processor register. This is a normal convention. Okay, that's how it is. This is a three address format. That means you can represent two source and one destination separately. But the problem with this occupies more memory space to represent and code it. So generally, most of the processors do not support 3 address format. Then coming to the next one, which is 2 address format, where you have operation, source, as well as destination, only this much. Okay. So simple thing is something like this. So let us say, suppose I write MOVE R1 comma R2. This is the 2 address format, easy way. So this is the first one, what I write is always the source. The second one, what I write is always the destination. So what is this? Actually, move is not move physically. Okay, this is like actually a copy operation. But the mnemonic is given as MOVE, but is actually copying. That means whatever is in R1 is copied to R2. That is whatever is in source is copied to destination, but source is not modified. Source contents are never modified. Destination contents are modified. Okay. So it is like a copy paste, not cut paste operation. Okay. So in 2 address format, this is easy. Okay. Because I'm just copying that one number to another number. Suppose I want to do this only, that z equal to x plus y. This I want to do now. Okay. This I'm doing a 3 address like this, easy. But if I want to do this using 2 address format, see, you can't write add x comma y comma z because you can't give 3 operands, right? You can give one source and only one destination. That means it's such a simple operation also need to be broken down into smaller steps. Okay, so in assembly language, the code length is more compared to high level language because each and every step has to be separately written, okay, based on the format which you are using. So I need this operation now, right? So what should I do is something like this. So this is one method of doing this. So what is the meaning? So I'll first copy, okay, x to z, let us say. X to Z. Anyway, Z is overwritten, Z is destination, right? Anyway, the data will be lost. So I don't worry about it. So first I'll copy X to Z. That means X value is already in Z now. Now I write add. So observe that I'm writing now properly Y comma Z. So what does that mean? Now in this case, Z also acts as a source because for addition, anyway, we know that minimum 2 numbers are needed or 2 operands are needed. So this means the operation is something like this now. So you are actually storing in Z what you are storing, what is in Y you are adding with what is in X, but X has been already copied to Z. So you are trying to do this. So before the operation, Z acts as source also. After the operation, the Z acts as destination to store the complete result. First time we stored one operand, same thing we used to add with another operand which is in Y. Then the result of these two will be stored in Z itself again. So there is no third operand to be mentioned. It is not possible because it's a 2 address format. Okay, so this is a limitation of 2 address format always. Okay, and as I said, source contents are not modified. Okay, hope this is clear to you. And go to the next one, 1 address format. This is much more difficult now because we can represent either source. This slash indicates you can represent only a source or destination, not both in this particular thing. Okay, so only one memory operand as source or destination can be mentioned, and the other is assumed to be in a special register of the CPU called as accumulator. Okay, it's assumed to be there only if the data is already available in accumulator. One more data you can specify with your mnemonic over here in the 1 address format. Okay, so again, if I take this example, okay, in 3 address format, it needed only one instruction, assembly language instruction. You can see in 2 address format, the same operation was having 2 instructions to complete. Now in 1 address format, you can see that this operation requires 3 instructions to perform. That is how assembly language implementation varies based on the formats what is available to us. So what is Z equal to X plus Y? Take 2 operands and add them and store it in Z. That's all. But I cannot now write even this way also. Move X comma Z is also not possible now. Because move X comma Z, if I write, what is the meaning? Suppose if I write like this, it means I'm specifying both source as well as destination, which is a two address format. But I'm trying to use now one address format. So I should represent only either a source or a destination. So we use special instructions called load and store. Load and store. Okay. So how it is done, I'll just explain the small diagram here just to understand. So just let us say, okay, let us say this is your CPU, your processor, and this is the memory. Okay. Let us assume that this is the location X with the address X. This is the location with the address Y, and this is the location with the address Z. So what is our thing? Suppose some data is there here, some data is there here. So you want to add this to data and then store this. This is the final question is, take the data from two memory locations X plus Y, add them. Memory cannot add, as you all know. So there is ALU inside your CPU, which is actually performing this operation, right? Something like this. So that means you should send that address using the address bus, use your read-write signals, and then get the data using data bus. All this is physically to be done. That's of course internally done. Let us not worry about it now. But the question is, in a single address format, we assume that there is a special register called accumulator, which is available. So when I do this load X operation, this data, whatever is there, will be automatically copied into, because accumulator is not mentioned, you can see here, it is not mentioned. So it is implicitly assumed that that is always there. So load means read. Load means read from memory. Okay. So 25, the data, assuming that 25 is the data available at location X. So this 25 is copied into accumulator. Okay. Then you have the add instruction, add Y. That means this 25 is already here. Okay. So when I say add Y, it means that this Y will automatically come to ALU. This 25 will also go to ALU. Okay. This is ALU. And then addition is done over here. And the result is available in the accumulator again. Is the assumption here. So suppose 25 plus 38, some number 53 or 63, whatever the number you get here, assume that after this addition, the result is getting back into accumulator only. So this will be overwritten. Now when I say store Z, something from accumulator is copied into the memory location Z. So one single instruction Z equal to X plus Y now needs three different instructions in assembly language. It looks a simple statement in high level language. Okay. So with the accumulator, we are able to do one operation at a time, either loading or reading or writing or doing any one arithmetic operation. Okay. This is what you're trying to do with this single address. Whereas in two address, you can specify one source and one operand. In three address, you can put two sources and one destination operand. The last one is zero address instruction. Zero address instructions are normally with respect to push and pop, that is stack operations, which you will discuss in module 2. Okay. Now let us say you'll take one example of writing a simple assembly language program using this one address, two address, and three address formats. Okay. So we'll try to understand how actually we can do this. So let us say the question is something like this. This can be again a simple 4 marks question in the exam. To write the program. So let us say there is a equation X equal to A plus B. This is multiplication star C plus D. Simple example. Okay. Assume that all are memory locations. So using three address how to write, using two address how to write, and using one address how to write. So we'll try to see it little carefully to understand, and remaining things you can practice other programs. Okay. So in a three address format, as we know that you can represent two source and one destination. So this is two sources. You are trying to add A and B, then you are trying to add C and D, then this result, let us say some P and some Q, let us say, these two you want to multiply. So there are three operations to be done now. 2 additions and 1 multiplication. So that's what is written here. So add a comma b comma f. Comma is important. Comma is the separator between operands. Okay. And after mnemonic, there is space. There is no comma here. Okay. So what it means, A is one source, B is another source, F is some temporary destination because my final destination is X, which needs this entire result. So what I'm doing now is I'm trying to add the content of A with content of B. So again, if I try to write the memory map for you to understand this, it looks something like this. This is, let us say, A, B, assume that we have written, C, and D. Okay, this is the memory structure. So better always you write a memory map to understand this operation, because assembly language is little difficult to understand compared to your C or C++. See, let us say this is F, this is some other something. So my final result should be in X. Let us say this is the thing. So I have some numbers here, say these are the numbers I want to do, 6, whatever, some numbers are there. Okay. So what is the first job? I want to do addition of these two numbers, which are at A and B locations, which I'll be doing with this instruction. And this partial result will be stored at, say, this F. Similarly, I want to add these two, C and D, with this instruction, the content of C and D. And this is a partial result. I'm storing at some G. Here I'm storing. Okay, but my final result should be in location X as per the equation given. So what I'll do, I'll take this partial result F and G and then store it in X. So I'll do multiplication of data available at F, data available at G, and then store that result in X. So 3 address format is easy, as we know, because you can represent 2 source and 1 destination in a single instruction. So that's the easiest way of doing this. So this is 3 address format. The comments are also written here. You can understand what I'm trying to do there. Okay. And with this memory map, it should be more easy to understand. Now coming to the 2 address format. As I said, 2 address format means you can specify 1 source and 1 destination. Okay. So that means you can't do all the operations together as in the 3 address format. So you need little bit more set of instructions. So first what I will do is add A comma B. Now, as previously explained, when I say add A comma B, this is source, that is destination, second one. But addition requires anyway 2 numbers. So it means actually add the content of A as well as B. B acts as source before the operation I said, right? So 12 plus 3 is added, and then result is stored again in B. That means this will be overwritten now. Clear? Earlier, I stored it in F and G separately so that ABCD was intact as it is without any modification. Now, since B acts as source as well as destination, after addition, the result is again stored at B only. Okay. Similarly here, add C comma D. Take the data from C and D, add them and store it in D itself. So D has a new data here after addition. So the new data is in B and D, then you multiply them using MUL or MULT, whatever we take, that in mnemonic is up to us, because we are not specifying any processor in this subject. Please remember, when you study higher semester subjects like microprocessor or microcontrollers like 8051, etc., there you will use specific mnemonic for that particular processor. Here we are looking into a general assembly language. So these notations can be changed. MULT also you can write instead of MUL. Okay. So MUL B comma D says whatever was in B and D you multiply and keep it in D only again. Because it's a 2 address format, you cannot write the third operand or third destination separately. So the result is in D again. So that, but you want the result in X. So you have to copy from D to X. So you of course, again, you can write move also, as I said, MOVE is also okay. MOV is also okay, but follow any one notation properly. Okay. So move D comma X. So copy from whatever the D result into X. So you need now 4 instructions instead of 3 instructions to do the same operation. Okay. So let us come to 1 address format. As we said, 1 address, we are little handicapped because only 1 operand we can mention in the instruction. Other operand is assumed to be an accumulator. So you need, and you can use only load and store instructions. You cannot use move, etc. for data transfer. Okay. So load A, add B, store F. This entire thing, what is this being done is this here. I have already shown you how that memory map and accumulator in the previous example. So copy from memory A to accumulator register, then add with accumulator the content of B, and then store it back again in accumulator only. In after addition, the result is here only. So that result you are again temporarily storing in F. So you did now A plus B with this. Similarly, C plus D. These three instructions for C plus D. Sorry, these two instructions for C plus D. Sorry, I'll just erase this. Okay, these two instructions for C plus D. Why? Because when you load C, accumulator content will be loaded with C. Then you're adding with D, your accumulator is accumulator plus D. That means the data is already in accumulator, right? So when I say multi F, what happens? What happens? Whatever is already in accumulator will be multiplied with F. F is this result. You can see A plus B result is in F, right? So you multiply the C plus D result, which is an accumulator, with A plus B result, and again store it in accumulator only. But you need the output in memory location X. So what you do, you store it in X, that is copy from accumulator to X, that location. So you need, now you can see 7 instructions to perform the same operation. So you need 3 instructions here, 4 instructions here, and then 7 instructions. It means the kind of coding effort varies based on what is the available hardware and the architecture for us. That is why assembly language has to be learned very carefully. Okay, so this is the example. I'll try to erase all these things and show you once again. So this is the example we tried to solve now. So you A plus B star C plus D you had, and with 2 address, 1 address, and 3 address, we have solved this. Same way, suppose we'll repeat example 1, when arithmetic operations on both memory operands are not allowed. So what's the meaning here? We have said that all this are memory. That means your X, A, B, C, etc. all are assumed to be memory locations, and we assume that data memory operands are allowed for all the operations. But there may be restriction in the architecture that directly memory operands cannot be taken for operations. So you may have to again modify this program in a different way. That means at least one operand must be in processor register. Okay. Then we'll change that instructions like this. So I wrote, if you remember there, add A comma B comma X, something like that. I said no, A comma B comma F, something we said like that. So the modification is little different over here. Okay, there is a small issue here. So actually it's wrong. As we know, A comma B comma R1, because destination is to be given later. So this is, so please look into this. This is R2. Okay. Then X. Okay. So if the question says that at least one processor register must be used to do the operations, then you should be able to do that way. And for one address, there is no change because anyway, already we use the accumulator. Okay. So why we need to use registers, why not memory directly, is something like this. Again, I'll show the diagram. Where are registers? As we know, CPU, and this is memory. And memory is an external device, right? External IC connected to CPU using buses. Again, remember that. So registers are here, right? Inside your CPU. And your AL is also inside the CPU, right? So what does it mean? It means if you take data from here and do it, the execution will be really fast. It doesn't take much time. Whereas if the data is here, so first CPU has to send the address, issue the read signal, then take this data. So there is memory access time involved. And if memory is slow, you take more time to even read the data itself. Then you will perform the operation. Again, storing that. So whenever you need fast operations, data must be available in registers. Okay, that means memory access the number of times the memory is accessed can be reduced, and you can do the operations faster. But only limitation is, you suppose you have 100 data, or you want to, let us say, find the topper in your class. So you will have to take all 50 students, store their marks, and then find out, compare and all. So to store 50 numbers, you need 50 registers then. So unfortunately, that is not possible with the design of the CPU. So number of registers inside the CPU are less. So if more data is there, then you need to anyway store it in memory. But if few data you want to operate, you can as well keep them in the CPU registers, and you can perform the operations in a faster way. Okay, this is how we try to understand why registers and memory both are important. For large data storage, definitely memory is needed. For fewer data, instead of memory, you can use only registers, and the operations can be done faster. Okay, this is how it is. So we are coming to the end of this session now. So there are some few questions for you to again recall the topics and then understand these things. For example, first question, easy question I have asked you. In RTN notation, left side of the arrow represents. So we have used, remember that? I'll just write again here, right? You remember on the RHS something and on the LHS something. So left side of the arrow is always destination here, right? Right side of the arrow is the source, something like that. Okay, and in assembly language notation, dash is used to represent the operation. Dash means what is used there. Don't write command, because command is called as mnemonics here. So mnemonics are used to represent commands or operations like that. So I have given you some simple program also to practice based on this, whatever we have written here, so that you'll be more comfortable in using this 3 instruction, 2 instruction and 1 instructions format. So just to recap, we started with instruction sequencing. That means all your instructions and data are stored in consecutive locations in memory. And then we identified what is register transfer notation and assembly language notation, and what are the different instruction formats to write an assembly language program to perform a simple task. Okay, so then we'll move on to the next session. Thank you.